Once again, welcome to another video about maths. This time it's GCSE maths. So this is going to be Edexcel Higher Tier Paper 1 from May 2019. And this is actually the first higher tier walkthrough paper I've done. Hopefully it'll be the first of many. Let me know how you found it by leaving a comment in the comments section and be as honest as you like. Although if it's not a favourable review, at least try and be quite respectful when leaving a comment, if you get my drift. Anyway, so there's 22 questions. I'm going to talk through them all, and for some of them I'll give multiple different approaches which you could use. So let's get started straight of all. I'll stop waffling on. Let's have a look. The first question, question 1. So it's a probability question. So we're told there are only blue cubes, red cubes and yellow cubes in a box. The table shows a probability of taking at random a blue cube from the box. So blue is 0.2, red and yellow haven't been filled in. But we are told here that the number of red cubes in the box is the same as the number of yellow cubes in the box. So that's saying that if you've got the same number of red and yellow, it stands to reason that therefore the probability of picking a red must be the same as the probability of picking a yellow. If there's the same number of each, then red and yellow are both equally likely to be picked. So complete the table. Well, for any probability question, the sum of all probabilities has to add up to 1. So here, we've got 0.2. So 0.2 plus the probability of being red plus the probability of being yellow must all add up to be exactly 1. But like I said earlier, the probability of being yellow is the same as the probability of being red. So 0.2 plus the probability of being red plus probability of being yellow, which is also the same as the probability of being red, p red plus another p red, I can say that's the same as 2 lots of the probability of being red. That equals 1. Subtract 0.2 from both sides. So 2 lots of a probability of being red must be 1 minus 0.2, which is 0.8. Therefore, the probability of being red is going to be 0.8 divided by 2, which is 0.4. And that's also the same as the probability of being yellow. So it's 0.4 in each box. Part B. There are 12 blue cubes in the box. Work out the total number of cubes in the box. And so we can use the idea of relative frequency here. Okay, so 12 blue cubes. 12 is represented by 0.2. Compare 0.4 to 0.2. Well, 0.4 is double 0.2. And so picking a red cube is twice as likely as picking a blue cube. Therefore, there must be twice as many red cubes as blue cubes, because 0.4 is double 0.2. So to keep it proportionally correct, we double 12. Double 12 is 24, so there must be 24 red and also 24 yellow cubes. So therefore, the grand total number of cubes in the box will be 12 blue plus 24 red plus 24 yellow, and that comes to 60 cubes. That's question 1 done. Question 2. Dion needs 50 grams of sugar to make 15 biscuits. She also needs 3 times as much flour as sugar, 2 times as much butter as sugar. She's going to make 60 biscuits. Work out the amount of flour she needs. So let's try and put this into more of a visualization problem. So she's making 60 biscuits, but we're told here about 15. Okay, so for 15 biscuits, we're told first off she needs 50 grams of sugar. So sugar's 50 grams. But now it says she needs 3 times as much flour as sugar. So flour, she needs 50, 50 and 50 again. And she also needs 2 times as much butter as sugar. So the butter needs to be double for sugar, which is going to be 50 grams plus another 50 grams, which is 100. However, she's going to make 60 biscuits. We need to work out how much flour she needs. Well, for 15 biscuits, that's the wrong colour, silly me. Flour I colour-coded as green, so I'll colour-code that in green. Amount of flour she needs. Well, for 15 biscuits, the flour needed was 50, 50, 50, that's 150 grams. 60 biscuits, 60 equals 15 multiplied by 4. It's 4 times as many biscuits. So you can think of it as she's making 4 batches of 15. So the flour she needs for 60 biscuits will be the flour she needs for 15 biscuits, which is 150 grams, multiplied by 4, which is going to be 600 grams. So flour, 600 grams. She also apparently has to buy all the butter she needs to make 60 biscuits. She buys the butter in 250 gram packs. How many packs of butter does Dion need to buy? So again, it's mentioning she needs to make 60 biscuits. Now we're talking about the butter, which I've colour-coded in this blue colour. For 15 biscuits, she needed 100 grams of butter. So for 60 biscuits, we can work out how much butter she needs to buy. The butter she needs is the 100 grams for 15 biscuits, but 60 biscuits is 4 times as many, so 100 grams multiplied by 4, she needs 400 grams of butter. But it comes in 250 gram packs. So 1 pack would be 250 grams of butter. That's not as enough as she needs 400. But 2 packs would be 500 grams of butter. 500 grams is at least 400, so 2 packs would do. So she needs 2 packs of butter. Question 3. There's a few different ways of doing this. I'll start with the most obvious, I think. Find the highest common factor of 72 and 90. So, first thing, method A, by inspection. This is something that's always worth considering when thinking of a highest common factor problem. And it's this. The highest common factor of a pair of numbers must also always be a factor of the difference between the numbers. So here, between 72 and 90, the difference is 18. So if we're trying to find the highest common factor of 72 and 90, we should also think of factors of 18. So 18 is a factor of itself, so let's try 18 first. Well, 72, that's actually 18 times 4, so 72 is also a factor of 18. And also 90. 90 is 18 times 5, so that works too. So actually, the highest common factor is 18. So always check the difference between the numbers and take factors of the difference. That, I think, is a quick way of often, not always, but often finding the highest common factor. For example, if 72 and 90 didn't have a factor of 18, we could try different factors of 18, for example 9, 3 and so on. So this one we could simply say highest common factor is 18. Another approach. factor bugs. Now this is a bit more of a simplistic way of doing it, but it's still worth recapping. The pressure of the exam can do strange things to your brain, so never forget the simpler ways of doing things as well as the more direct ways. So what I mean by factor bugs are when you do like a little spider diagram almost, with factors branching off from the number in the centre. So let's start with 72. The smallest factor of any number is 1. So on one side, I'm going to write down what I'm dividing the number by. On the other side is the answer to that division. So 72 divided by 1 is 72. That's my first factor pair. Next, go up a number. So this is even, so I can divide it by 2. 72 divided by 2. So 2's into 7 go 3 times. 2 times 3 is 6, so 1 left over. And 2's into 12 goes 6. So 72 divided by 2 is 36. Go up a number. Can I divide it by 3? Well, it turns out, actually, yes, you can. As you can see already, this way is longer. But as you'll see, you'll still be able to get your marks. 3 into 7 goes 2, remainder 1. 3 into 12 goes 4 times exactly, so 72 divided by 3 is 24. You can find the others doing division in a similar way. You can also divide 72 by 4. That'll give you 18. You can't divide it by 5. You can, however, divide it by 6. 72 divided by 6. That would give you 12. You can't divide it by 7. You can divide it by 8. And that gives you 9. Any higher, I arrive at the numbers on the other side, so that shows I've got them all. So these are all the factors of 72. I'm going to do 90 a bit quicker now. Divide it by 1, we get 90. Divide it by 2, we get 45. Divide it by 3, we get 30. Can't divide it by 4, can divide it by 5, which gives us 18. Can divide it by 6, that gives us 15. We can't divide by 7 or by 8. We can divide it by 9, which gives us 10. Bigger than 9 is 10, which we've already got on the other side, so that's all the factors of 90. So now the highest common factor is the largest number we can see in each list, which hopefully you can see is 18. Therefore, the highest common factor of 72 and 90 is once again 18. And finally, the third approach, prime factorisation. This is a bit quicker than method B. So method C, we start with 72 and split it into its prime factors. These are often called prime factor trees. So divide 72 by anything. I tend to divide by 2 if I can. I get 36. And if you get a prime number, circle it. 36 isn't prime, so I can go again. I could divide it by 2. Half of 36 is 18. 2 is prime, so circle it. 18 I can half, which gives me 9. 2 is prime, so circle it. 9 isn't. I could divide it by 3, which gives me 3. So therefore, 72 equals 2 times 2 times 2, because I've got 3 2's, times 3 times 3. So I also now do the same with 90. This method is particularly good when you've got bigger numbers to consider, and can also be extended to doing lowest common multiple questions. Ask your teacher if you're not sure what I mean by this. So now we're going to do 90. 90 can be halved, which gives us 45. I can't half 45, but I can divide it by 5, which is prime, so I circle it. That gives me 9. And 9 can be divided by 3, which gives me 3. So now I can write 90 as a product of its primes. So 90 equals 2 times 3 times 3 times 5, doing it in order of size. So 2 times 3 times 3 times 5. Now what we do is we pair up the common prime factors in each. So 90 has 1 2 in it, so compare that 2 with that 2, so they're paired up. There's no more 2s you can pair up, sadly. Compare that 3 with that 3, and that 1 with this one. The 5 I can't pair, and these 2s above I can't pair with any 2s down here. So that tells us that the highest common factor is 2, 3, 3 multiplied together, which of course is 18. So take your pick from any one of those 3 methods I've shown you. If you can spot the first one, as you can see, it's definitely the quickest one to go for. Question 4. So the diagram shows a plan, front elevation and side elevation of a solid shape drawn on a centimetre grid. That's important, it's a centimetre grid. So it says in the space below, I'm going to do mine to the side, just because it fits onto the screen. Draw a sketch of a solid shape. Give the dimensions of the solid in your sketch. Okay, so the plan means how it looks from the top down. So the plan here is clearly circular. So it's something circular as looked at from the top. So that's the first thing I'm going to do. Okay, so the plan is going to be circular. So I'm going to cheat here. If you sketch it, that's absolutely fine, of course. But I'm going to do a circle, like so, and then I'm going to squish it in so I can draw it in like a 3D sort of way. Okay, so that's going to be the top. I'm going to colour it in as well. So I'm going to colour it in the yellow, like I have here. I'll have dimensions in a bit. Now here, the front elevation is exactly the same as the side elevation. So it's going to look the same no matter which way you view it. So the shape this actually is a cylinder. If you turn a cylinder, imagine like a can of Diet Coke or a can of Coke or whatever, a beer can when you're old enough, who knows. What you can do here is if you imagine turning a can round, it'll always look the same width no matter how and where you turn it. So this is actually a cylinder here. So now all we need to do is to finish off the sketch by doing lines down the side like so. Excuse me. And the same on the other side. And this is where I personally struggle, just trying to do a curve joining these bottom 2 bits. So something like this. So what we've not done here is given the dimensions. This is a centimetre grid, okay, and so that means that the full width across is going to be 1, 2, 3, 4 squares, which is 4 centimetres. So that's 4 centimetres of the height, 1, 2, 3, 4, 5. And so, give units as well, 5 centimetres, and that's 4 centimetres. I'll put a bit closer to actually, like so. And I suppose, if you really wanted to impress the examiner, what you could do is say that the radius of the circular top is 2. But as a bare minimum, do the sketch, label the height as 5, the width as 4. That's all we need for question 4. Question 5, we've got this translation. So it says shape A can be transformed to shape B. So really important, so you don't get the wrong way around. we're going from A to B. And so the way round we're going is from here to there. Do not lose marks by thinking it's from B to A. Now let's read it carefully. So first of all, it's saying we can do a reflection in the x-axis. And so if we were to reflect this shape in the x-axis, let's just think of how that would look. So label that corner a blue corner. This one can be red, and this one here would be green. Now when we reflect a shape, it reflects at a 90-degree angle to the mirror line and comes out an equal distance away on the other side of the mirror line. That's how you work out where the image goes. And so this one here, the blue, is 2 squares away from the x-axis, so it'll end up being 2 squares away on the other side once it's been reflected. The direct distance of the red corner here from the mirror line is, as we can see, 2 squares away. So if we then just reflect it in the x-axis and go 2 squares on the other side, we'll end up here. And finally, this green one is 1, 2, 3, 4, 5 squares away from the mirror line. So go 5 squares away on the other side. 1, 2, 3, 4, 5. It's going to end up here. In terms of imagining it a bit nicer, I suppose you could say, it's going to be something like this. Now the green will overlap slightly with the blue, but it's going to be that sort of shape. Now we just join the points together, and we've visualized the first part of this problem. So that's the first step. Now, after reflection, we can translate by column vector C, D. So C means how far to the right we go, D means how far up we go. So to go from this image here to B, let's just think about this carefully and we'll be absolutely fine. Okay, so there's the shape in case there's any doubt or your screen's not very clear. So how can we go from this yellow to B? Let's just think about that. And what I'd suggest we do is we pick any corner and the corresponding corner on the final image. I'm going to go for the right angle here. That right angle ends up going here. Get rid of that line for a moment. So let's just consider this. So this corner, how far do we move along? So we go 1, 2, 3, 4, 5, 6 squares to the left, and then we go 1 square down. So 6 left and 1 down. In terms of column vectors, with a column vector, the top number means how far we move to the right. These are like coordinates, but given top to bottom rather than reading left to right. So how far along, how far up? 6 left means minus 6 units to the right. And the bottom number, the D, means how far up we're going. So if we're going 1 down, that's minus 1. So in other words, our C is minus 6 and our D is minus 1. Question 6, good old ratio question. So we've got a shop selling packs of black pens, packs of red and packs of green. And we're told that there's 2 pens in each pack of black pens, 5 pens in each pack of red, 6 pens in each pack of green. So we've got a ratio now, not of the number of pens, but the number of packs of pens. So what we need to do here is think what these numbers mean. So number of packs of black is 7 packs, number of packs of red, 3 packs, number of packs of green is 4 packs. This is a ratio of number of packs of different colours. What we need to do is translate this into a different form. And the form we need this in is how many actual numbers of pens. So what we need to do here is take these numbers and change them. So 7 packs of black pens, but it does say here there are 2 pens in each pack of black ones. So as a ratio, 7 packs, 2 pens in each pack. The total number of black pens as a ratio would be 7 multiplied by 2, which is 14. Then number of packs of red pens is 3. However, we're told here that there's 5 pens in each pack of red ones. So similarly, what we need to do here is again change this number as well by multiplying it by 5. 3 packs of red ones, but there's 5 pens in each one of those 3 packs. So 3 times 5, that gives us 15. And finally, number of packs of green pens as a ratio here is 4. However, just as there's 5 pens in each pack of red, there's 6 pens in each pack of green ones. And so if 4 packs of green pens are sold and there's 6 pens in each one of those packs, that's going to be 4 multiplied by 6, which actually be 24 green pens. Not packs of green, but 24 actual green pens. So this here is a ratio of actual numbers of pens. Whereas what we had to begin with was number of packs of pens. And so this here is much more powerful to work with. So now what we need to do is to translate this into a table, perhaps. We could also use a bar model, but I'm going to do this as a table. So as a ratio, it's 14 black pens to 15 red to 24 green. So if it were 14 black pens and 15 red and 24 green, if we added these numbers up, what we'd get is a total of how many this comes to. And that would come to, let's work it out, it'd be 53. If you're not sure, just do it like this. Column addition. 4 plus 5 is 9, plus another 4 is 3. Try over 1. 1 plus 1 plus 2 is 4, plus an extra 1 is 5. But actually it does say here that the actual total number of pens that were sold wasn't 53. It was actually 212. So the pens were sold in this ratio of pens for colours, but the actual total wasn't 53, it was 212. And so what we need to do is to use proportional reasoning to jump from 53 up to 212 and follow exactly the same procedure for these other numbers here. So what would you need to multiply 53 by to get to 212? Well, the answer here would be we need to multiply all numbers in this ratio by 4. 53 times 4 gets us to where we need. If you're not sure about that, just think of the 53 times table. Double it, we get 106. Add another 53, it'll be 159. Add another 50 and another 3 will get us to 212. So 1, 2, 3, 4. So you need to multiply all these numbers by 4. I'll say we need to, and it's a slight untruth. We don't. We're only interested in the number of green pens sold, really. But for completeness, I'm going to multiply all the numbers by 4 just so you can see. So 14 multiplied by 4, that would be 56. 15 multiplied by 4 would be 60. And 24 multiplied by 4 gives us 96. And so the number of green pens sold is 96 green pens. And that's our final answer for question 6. Let's now move on to question 7. In question 7, we've got 2 rectangles. So let's label on what we know about these rectangles. We're told that QR is 10 centimetres. So the first thing I'd like to do is to label on that QR is 10. QR means from Q down to R, so we're looking at this here. So from Q to R, that's 10 centimetres. However, because it's a rectangle, we know that the opposite sides of a rectangle are equal in length, so we can also say that from P to S must also be 10. I'm also told that BC equals PQ. And so this side here from B to C, which of course will be the same as from A to D, because that's a rectangle as well, that's the same as from P to Q. I apologise about my throat. Can't seem to get my throat clear. From P to Q, because it's a rectangle, it will be the same as from S to R. Now, we're told the perimeter of ABCD is 26, and we're told that the area of PQRS, this one here, is 45 centimetres squared. It says find the length of AB. So from A to B, is this here, which of course is the same as that there. So if we just think about PQRS, so the area of PQRS, and that's going to be the length of it multiplied by the width. So it's going to be 10 multiplied by PQ, but we're told that the area of PQRS is 45. So therefore, PQ must be 45 divided by 10, which must be 4.5 centimetres. So double check, 10 times 4.5 would give this area of 45 centimetres squared. So now we can fill this in and add it to our diagram. So we've worked out what PQ is. PQ is 4.5 centimetres. So that's 4.5. And because BC was the same as PQ, we can say this here is 4.5. Going back to this bit now, the perimeter of ABCD is 26. So using what we just worked out here, the perimeter of ABCD, that's just the length all the way around the shape. So it's AB plus 4.5 plus DC plus 4.5. We're told that equals 26. So AB, as you can see here, is what we're trying to find. DC is the same as AB, And the 4.5 comes from working out what PQ was. So what we can do here is we can simplify this. So 4.5 plus 4.5 is 9, but because DC is the same as AB, I can say this is 2 lots of AB. Because AB plus DC is the same as AB plus another AB, which is 2 lots of AB. So 9 plus 2 lots of AB is 26. If we now subtract 9 from both sides of this equation, we'll see that 2AB must equal 17. Therefore, AB is going to be 17 divided by 2, which is 8.5 centimetres. And that's question 7 sorted. Question 8 comes in 3 different parts, and each part relates to place value understanding. Part A, we're asked for an estimate for the value of the square root of 63.5 multiplied by 101.7. Now, your teacher will explain what an estimate means in different ways, but it all means the same thing essentially. An estimate is an educated, good guess in terms of what the answer will be close to. Another way I like to think of an estimate is something that can be done without a calculator. Okay, at GCSE level, that's how I would think of an estimate, something you should be able to do without a calculator. So here you can see it's about a square root. Now, I don't know about you, but I would struggle to square root numbers unless I'm trying to square root a number which is a square number. So for example, I know the square root of 4 is 2, because 4 is a square number. Ask me to do in my head the square root of 77, I'd be really struggling. So if you want an estimate of this, what I would suggest to do is to try and get what we're square rooting to be, if we can, a square number. Now, in terms of square numbers, we can think about this together. For example, 63.5, that's very close to 64, and 64 is a square number. So we can think of this as rounding this to the nearest whole number, which is 64, and that's absolutely reasonable. We're not changing the value of 63.5 much if you round it to 64. In the same way, 101.7, you can think of this as rounding it to the nearest 10 if you'd like, and if we did that, we get 100. And again, 100 is a square number. So if we do this, it actually makes it much easier for us, rather than trying to work out a difficult calculation. Remember, an estimate should be something we could do fairly comfortably without a calculator at GCSE level. 64 multiplied by 100, that's 6,400. Okay, so the square root of 64 is 8. So the square root of 6,400 would be 80. Another way we can think of this is to use the law of surds. If you don't like this way of thinking about it, we can think of 64 times 100 as root 64, root 100, and partition the square root. The square root of 64 is 8, square root of 100 is 10, 8 times 10 is 80. Now, 80 isn't the only valid answer. As long as you get an answer which is between 75 and 81, the examiner would award you the mark, but I think the most obvious way of doing this would be to try and get the numbers to be square numbers and square rooting from there. Part B, we're told that 2.3 to the power 6 is 148 correct to 3 significant figures. We're asked to find the value of 0.23 to the power 6 correct to 3 significant figures. Well, one thing I'd suggest we do here is to think about what 0.23 is in relation to 2.3. And that's to say that 0.23 is 2.3 divided by 10, which is the same as saying 2.3 over 10. So by rewriting 0.23 in this form, we can do this much better. So 0.23 to the power 6 we can think of as 2.3 over 10 to the power 6. Then we can use the laws of indices to do the rest. So if we raise a fraction to a power, that's the same as the top to the power 6, whatever power we're raising it to, in this case it's a 6, all over 10 to the power 6. Now 2.3 to the power 6 we were told is 148. So we're using the information we've been given in the question. At the bottom, 10 to the power 6, if it's a power of 10, we simply write a 1, and the power tells us how many zeros come after the 1. So 6 zeros. So that's 1, 2, 3, 4, 5, 6. We're dividing 148 by a million. So the way we do this is, or the way I do this, is as follows. If we multiply or divide a number by a power of 10, either a positive or negative power, the answer will always look like the number itself. So the answer is going to look like 148. Now what I would suggest we do is we put some zeros in. Because we're dividing by a big number, it's going to be 0 point something. The answer is going to be pretty tiny. So I'll be sketching in some zeros like this. Now, 148 means 148.0. If it's a whole number, the decimal comes after the units. So what I'm going to do here is I'm going to put the decimal of 148 at the end. That's where it's starting. Now, if we're dividing by a million has 6 zeros. That means we're going to move this decimal point 6 units to the left. Okay, so we're going to move it 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So try the answer a bit nicer. That's 0.0000148, like so. Finally, for question 8, part C, find the value of 5 to the minus 2. This again is laws of indices. So any number to a negative power is the same as 1 over this number with the power changed to its positive form. So 5 to the minus 2 is the same as 1 over 5 to the positive 2. In other words, 5 squared. 5 squared is 25, so 1 over 5 squared simply means 1 over 25. Question 9. I'm going to show this in one of two different ways. The first way is by far and out the way I'm recommending. I'm going to show you a visual way after, which to be honest I'm not recommending, but it might help your understanding of why it works, this method I'm going to show you next. So we're multiplying two fractions. These are mixed numbers as well. We're asked to give the answer as a mixed number in its simplest form. So the first method, direct arithmetic, this is definitely the way I would advise you try to do it. So the first step is we change these into top-heavy fractions. Okay, so 3.5 multiplied by 1 and 3/5. So once you change 3.5 into a fraction all over a 2. So we've changed to a top-heavy fraction, we don't change the denominator. The way we do it is we multiply the whole number by the denominator, and then we add on the denominator. So 3.5 becomes 7 halves. It was a 2, it stays being a 2. And the same process to change 1 and 3/5 to a top-heavy fraction. So we do 1 multiplied by the 5, and then we add the 3 on the top. So just to say we're timesing. So 1 times 5 is 5, plus the 3 gives us 8. So we now have 7 halves multiplied by 8/5. At this stage, we just multiply the tops and multiply the bottoms. So we just multiply going across. So 7 times 8, all divided by 2 times 5. Seven times 8, that's 56. 2 times 5 is 10. We now see if we can either simplify now or simplify later. Actually, I'd suggest simplifying now, just to make sure you don't forget to do it as a last step. So what we can do, both numbers are even, we can divide both top and bottom, numerator and denominator, by 2. So if we half 56, we get 28, and if we half the 10, we get 5. Finally, to give it as a mixed number, we see how many times 5 goes into 28. How many times does 5 fit into 28? It fits in 5 times. 5 times 5 is 25. 25 is 3 away from 28, so we have 3 left over. And that 3 is the numerator on the final fractional part of a mixed number. So we've got 5 and 3/5. That is a method I would strongly endorse you use. I'm just going to show you a visual representation of what's going on behind the scenes. So this isn't always practical, so I'm not recommending this, but it's just to sort of show you what's going on here. Okay, so first of all, what we're doing, we're multiplying 3.5 by 1 and 3/5. So as you can see, the main fraction we're talking about here is halves. And so I'm going to split going downwards into halves. And so 1 square is going to be a half. So a half, 1, 1.5, 2, 2.5, 3, 3.5, 4. So going downwards, I've got 1, 2, 3, 4. And then because it's 3.5, that's where 3.5 is along here. Now 1 3/5 is talking about fifths as a main fraction. So long ways, I'm going to say that each little square is a fifth moving along. So 1/5, 2/5, 3/5, 4/5, 5/5. That's 1 unit. And at the end, that's 2 units. So if that's 1 and that's 2, then 1 3/5 is going to be 1, 1 1/5, 1 2/5, 1 3/5. We're going to be looking here. Now, this visual representation, I want you to think about how you find the area of a rectangle. These are rectangles, as you can see. The area of a rectangle is the length multiplied by the width. In other words, it's just one number multiplied by the other. So we can imagine this as working out the area of a rectangle, which is 3.5 multiplied by 1 3/5. In other words, it's this area here in the top left of this squared grid. So if I just say it's equal to something in blue, where the blue stuff is all of this in this corner. And I can't stress enough, I'm not suggesting you do this in an exam, I'm just trying to let you see that it makes sense and relating it to previous stuff you've covered, in this case, areas of shapes. So each 5x2, each set of 10 squares is 1 square centimetre. For example, that's 1 across, that's 1 down. So this one in the top left, that's got an area of 1. So each 10 squares equals 1 centimetre squared, including, according to this system we've set out. So we've got 1, 2, 3 whole sections here. So that's 1 unit, 2 units, 3 units, plus fractions of other bits as well. So what I've got here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's 4. Then this 6 here, plus that 4. So I've got 1, 2, 3, 4 from these 2 bits, 5 whole units, and this bit left over here, which isn't quite a whole unit, that's 6 squares out of 10 of another unit. That's just that fraction of another full unit. But 5 and 6/10, I can simplify 6 over 10 to 3 out of 5. So it does work. It's not just like mental arithmetic magic with no logic behind it. That's why these rules are taught to you. It's a quick way of doing this stuff which is going on behind the scenes. You couldn't draw a grid very easily for, say, 27.5 multiplied by 82 1/5, could you? But that's what would be going on in some sense of a word. So that's question 9 done, and hopefully explained with a bit more clarity. So I hope you found that useful and not too confusing. Question 10, a good old graph. So we've got 2 straight line graphs with equations 3y plus 2x equals a half, and a second one, 2y minus 3x equals minus 113 over 12. They've both been drawn on the grid here. So I'm just going to colour code these, then we can work out which is which, though actually, when it comes to it, we don't really need to know. So if we were to rearrange this in terms of y, we'd subtract 2x on both sides, then divide by 3. So this one would actually end up having a negative gradient. So this one here, another way of thinking about it is the y-axis intercept here will be positive. This one, the yellow, is this line here I'm just drawing down now. And this one here, if you arranged it into y equals mx plus c, would be adding 3x to both sides, and so the coefficient of x would be positive. This must have a positive gradient. This line is the only one which is positive, and so this one I've highlighted in green will be this one here. So it says here, using the graphs to find estimates of the solutions to these simultaneous equations, where 3y plus 2x equals a half is true, and also where this one is true. Now this is actually much easier than what it seems. These equations look awkward. You might be panicked in an exam and think, oh, these equations are really hard to rearrange. These numbers are horrible without a calculator. But actually, all it means is the solutions will be where these two lines intersect. So the solution, or solutions, there's going to be one solution because there's only one point of intersection. It just means where the lines intersect, where they cross over. That's all it means. So we can estimate this quite well based on the fact that we've actually got a diagram which is fairly accurate. So we can go up here to estimate the x-coordinate where they cross over, and we can go along here to find out the y-coordinate of where they cross over. So they're crossing at this point here, and by my estimation, the x, as far as I can see, looks to be about 2.25. If you disagree slightly, that's fine. The examiner will give you a range of valid options for x. As long as it's close to 2.25, that's okay. And the y-axis here, it's obviously minus 1 something. So that looks pretty close to me to be minus 1.3. And that's all we need to do for that one. We just read off and find the x and y coordinates at this point here where the two lines cross over. Question 11. A bus company has recorded the ages in years of the people on coach A and the people on coach B. So here we have the ages of people on coach A. 23 people on coach A. We now have to complete the table below here to show information about the ages of people on coach A. There's 23 people. Now the examiner's been slightly kinder than what they could have been. If we have a quick read through here, just double check, these are in numerical order. So copy and complete the information here if you want to. You don't have to. In fact, we can just complete the information which is missing. So we need the median and quartiles essentially. So what we can do here is work out the median by working in from end to end. I'll give you another way after, which is much more direct, but I'm just going to assume you may have forgotten this or you might be panicked in the exam. Median is the middle number, so let's work in from end to end. So at the lower end, it's not going to be the first 4 obviously. At the higher end, it's not going to be the highest 4. Keep going, cross off another 4. 1, 2, 3, 4. 1, 2, 3, 4. Cross off 1, cross off 1. Cross off 1, cross off 1, cross off 1, cross off 1, and hey presto, we see actually that the median is this number here sticking out. So the median for coach A is 59. So now what we need to do is to work out the quartiles. Once you've got the median, what we can do here is consider 2 wings either side of the median. So we've got a left wing. It's not literally a wing, obviously it's not a bird, but I imagine it's a bird. So we've got these numbers here, left of the median, and we also have these numbers on the other side to the right of the median, which I'm underlining in green. The lower quartile is the median of the left wing. The upper quartile is the median of the right wing. Not talking about politics, just talking about either side of the median. So again, looking at the left, we can cross off as we go, working towards the middle of this left wing. So not the end ones, 1, 2, 3, knock off the other side. Not that one, or that one, not this one, or that one. But indeed, we're left with 53. So the lower quartile is 53. I'm doing the same with the upper quartile. 1, 2, 3, 1, 2, 3. Knock off this one, and that one, and this one, and that one, and as you can see, the upper quartile is 66. So that's one way of doing it. I did mention I'll show you another way. If you've got discrete data, where it's certain values, which is countable, so for example, people are discrete in terms of, not if they're loud or quiet, but with discrete data because it's countable. You can count the number of people in a room. You can't have half of a person or 0.231 of the people. There's certain values of people that can be taken only. So for discrete data, like we've got here, for median, I'll say here if there's n values. For median, you take a number of values, add 1 to it, and divide by 2. It's that number value. The lower quartile, add 1 to the number of values, divide it by 4, and similarly the upper quartile is 3 lots of this. It's 3/4 of the way along. So you add 1, divide by 4 to find your lower quartile, add 1, divide by 2 for the median, add 1, divide by 4, then multiply by 3, that numbered value is your upper quartile. So in our case, 23 people, add 1 and divide by 2, the median is the 12th value. This one is the 6th. This one here would be the 18th. If you double check, it's exactly what we've got. 1, 2, 3, 4, 5, 6th value, 7, 8, 9, 10, 11, 12th value, the median, 13th, 14th, 15th, 16th, 17th, 18th value, for the quartile here. So there's a couple ways of doing it. This way is quick if you can remember to add 1 and divide by certain values to work out your medians, lower quartiles and upper quartiles. Or you can use this silly idea of the median being like a bird. You've got a left wing and a right wing either side. The median of each wing either side tells you the quartiles respectively. Part B, we've now got some information about another coach, Coach B. So I've highlighted Coach A in yellow, Coach B in green, and Richard comes along and makes a statement. He says that the people on Coach A are younger than the people on Coach B. Is he correct? Give a reason. So I can't just say yes or no, I need to explain why. Well, let's have a look at this one. The main thing here is to compare the median. The median tells you a typical, on average, value of a typical person in a population. So the main thing here is the median for Coach A is lower than the median on Coach B. That would be tending to say that, in general, on average, people on Coach A are actually younger than the people on Coach B, because a median, a measure of like a typical average value, is lower on that coach. But more than that, weirdly, if you compare all the values, all the statistics we've got, every single value on Coach A is lower than for Coach B. The least age is lower than on Coach B, upper quartile is lower than Coach B, the lower quartile on A is lower than the lower quartile on B, and the greatest age, again, is less on Coach A than it is for Coach B. So we can say something along these lines to get the mark. So essentially say yes, or yes, he's correct, or he is correct, something to agree with him. Then because the median age for Coach A, and I put in brackets, and in fact all statistics for A, is lower than the median age for Coach B. Part C is quite similar as well. This time, Richard's saying that the people on Coach A vary more in age than the people on Coach B. So variation, essentially we're talking about spread or range, what we need to do here is compare the interquartile range I'd be suggesting for both. Okay, if you really wanted to, you could compare the overall range, but I think here the interquartile range is a better figure to be comparing. So is he correct? Give a reason. Well, let's work out the interquartile range for A. Interquartile range for A, that's the upper quartile, which is 66, minus the lower quartile, which is 53. That gives us 13. Whereas for B, the interquartile range for B is 73 minus 54, which is 19. So the spread of ages is actually greater for coach B than it is for coach A, because the interquartile range for B is higher than the interquartile range for A. So actually, the ages vary more in coach B than they do for coach A. Richard is saying the opposite. Richard's saying that the people on coach A's ages are more varied than on coach B. So actually, he's wrong for this reason of working out the interquartile ranges. As I say, if you really wanted to, you could have worked out the overall ranges, greatest take least, it'd be the same conclusion. So our reasoning here should be something along the lines of this. No, he's not correct, because the interquartile range for coach B is greater than the interquartile range for coach A, and give these numbers to back up your claim. These numbers here show you've worked it out. That will help you to get all the marks you deserve. Question 12, we've got 3 spheres. So there's a couple of ways of doing this. I'm going to show you 2 main ways. So it says the volume of sphere Q is 50% more than the volume of sphere P, and it says the volume of sphere R is 50% more than the volume of sphere Q. Find the volume of sphere P is a fraction of the volume of sphere R. So essentially we don't know the actual volumes of any of these. Okay, so one way of doing it, which I think might be a slightly harder way, is to call the volume of sphere P x. The great letter for anything unknown in maths or algebra is an x. The volume of sphere Q is 50% more than the volume of sphere P. 50% more means an increase of a half. So what we do here is multiply this by 1.5. X times 1.5, that's 1.5x. But then, sphere R is 50% more than the volume of sphere Q as well. So multiply by another 1.5. 1.5x times another 1.5, that'll give us 2.25. I'll show you why if you're not sure. Okay, so treat this without decimals first, put the decimal point back in. 5 times 5 is 25. 5 times 1 is 5, plus a 2 we've carried is 75. Same idea again, but put a 0 down, because this 1 is to the left of the first number. 1 times 5 is 5. 1 times 1 is 1. Add up, we'd get 225. Here, there's one number after the decimal. Here's another number after the decimal. So 2 decimal places in total. So in our answer, we need 2 decimal places. So the decimal point goes here. So here, this would be 2.25x. So the volume of P as a fraction of the volume of R will be x over 2.25x. Okay, so the x's cancel straight away. So you get 1 over 2.25. But fractions, really, you should avoid having decimals if you can. So what could I multiply 2.25 by to get rid of the decimal in there? Well, I could multiply both top and bottom by 4. 0.25 is a quarter, so this means 2 and a quarter. 2 and a quarter multiplied by 4, well, 2 times 4 is 8, a quarter times 4 is 1, 8 plus 1 is 9, and 1 times 4 is 4. So volume of P as a fraction of volume of R is 4/9. Okay, I'm going to show you an alternative though. And the alternative is, instead of picking x, just make up a number. Make up a number for what P might be. Doesn't matter what number you pick. Make it a nice, easy number to deal with. So for example, let's say P was 20 cm cubed. Times this by 1.5, 20 times 1.5 would give us 30. And 30 times 1.5 will give us 45. So the alternative would be to just make up a number for what P might be, but follow the same idea. So in this case, P is 20, R is 45, so 20 over 45. Then simplify that. I could divide both of these by 5. So 20 divided by 5 is 4. 45 divided by 5 gives us 9. So that becomes 4/9 as well. So either treating it as an algebraic x for a general unknown or picking a specific example, we get 4/9 either way we want to do this. Question 13 is a proof question. Given that n can be any integer, such that n is greater than 1, so if it's an integer greater than 1, it just means n is a whole number. It says now prove that n squared minus n is never an odd number. Well, n squared minus n, what we can do here is factorise this. Both have a common factor of n. So it says n brackets n minus 1. So using the fact that it's n brackets n minus 1, we can think about what this means. N minus 1 is 1 less than n. And so this is the product of two consecutive whole numbers. So n minus 1 is the product of two consecutive whole numbers. So therefore, n minus 1, if n is odd, this means odd times even. If n is odd, take 1 off it, that'll be an even. An odd number times an even is an even. Or, if n is even, then n times n minus 1 will be an even times an odd number, but any even number times an odd number again is an even. So therefore, n squared minus n is always even and never odd. Question 14. Find the exact value of tan 30 multiplied by sine 60. Give your answer in its simplest form. Now, chances are, if you're doing higher tier maths, you've probably been shown a table of exact trig ratios for sine, cos, tan of 0, 30, 45, 60 and 90. I'm going to assume you've forgotten this in an exam and maybe you're panicking and not sure how to remember yourself what they are. Obviously, in an ideal world, you'd memorise them off by heart, and there'd be no thinking involved, but the world is often not ideal, so how could you save yourself if you'd forgotten what they were? I'm going to show you two main ways. So method one is you can sort of, with a bit of thinking, a bit of deep thinking, you can actually derive them yourself. I'll put in brackets, this is challenging because it's not that straightforward. But in terms of trigonometry, it's SOHCAHTOA. So start with sine, cosine, then tangent. Okay, and again, you need to remember what the main values are. Okay, so the main value, the first one is 0, it goes up to 90. So we need to work out sine, cos, tan, 0, 30, 45 degrees, 60 degrees, and 90 degrees. So starting with sine, you can work out the rest, but I'm going to show you how. If you imagine the sine graph, you do need to know something. So if you remember the sine graph, so this axis is sine x, this is x. Starting from 0, it goes up from 0 and flattens out at 90. So we can use this as a basis of working out what sine of from 0 to 90 is. So when the angle's 90, sine x is 1. So when it's 0, when x is 0, sine x is 0. When it's 90, it's 1. Then what we're going to do, as you can see, it rises each time, so you get to 90, then it drops after. I want you to write down root 1, root 2, root 3. Like so, and divide them all by 2. That's your starting point, and then from there you can do the rest. So as long as you can remember the graph of sine, that it starts at 0, goes up to 90 when it's 1. So 0, 1, then root 1, root 2, root 3, all over to in the middle. You've got it now, because for cos, all you need to do for cos is to reverse it. So do the exact opposite for cos. So 1 here goes to 1 there. You write them now in descending order. So then it's going to be root 3 over 2, root 2 over 2, root 1 over 2. I know root 1 is just 1, but it's just a way of remembering it easier. And then 0 goes there. Then for tan, you just need to remember that tan is defined as being sine over cos. If you go and do A-level maths, this is a really important one to know. Tan is sine over cos. So we just do the sine number, divide by the cos number for each of these. So when the angle is 0, sine over cos is 0 over 1, that's just 0. This one here, we're going to have root 1 over 2 divided by root 3 over 2. The other two bits will cancel. It's going to be root 1 divided by root 3, so that's just going to be 1 over root 3. This one, any number divided by itself gives us 1. This one, root 3 over 2 divided by root 1 over 2. The over 2 bits will cancel, so root 3 divided by root 1 means root 3 divided by 1, that's just root 3. And this final one here, 1 divided by 0, the universe explodes if you try to divide by 0, so just, no. It would go towards infinity as your angle goes towards 90, but we can't actually use the exact value of 90 to evaluate tan when the angle is 90. So now we've derived all the ingredients we need. I'll show you another way after of getting to the same end destination. So we want tan 30 times sine 60. Well, tan 30 is this one. Sine 60 is that one. So now tan 30 times sine 60 equals 1 over root 3 multiplied by root 3 over 2. Now the root 3 on the bottom will cancel with that root 3 on the top, so we're going to get exactly 1/2. So tan 30 times sine 60 is actually exactly a half. Next, another way of thinking about it. We could use what's known as a 30, 60, 90 triangle. So this is a way of doing it via geometry. And so before we get a 30, 60, 90 triangle, one thing I want to do is just to draw an equilateral triangle. Okay, so this one, imagine it as equilateral, and I'm going to do all sides here as 2. So an equilateral triangle where each side is going to be 2. So the bottom side is going to be 2, but what I'm going to do here, I'm going to split it in half going down the middle. Okay, so equilateral triangle, each angle is going to be 60, including the top angle there, 60. But if I split it going down the middle, then this will be a right angle, and this angle will be bisected and become 30. And more than that, this used to be 2, and now the bottom side here, from there to there, that will just be 1. So now we can work out tan 30 and the rest of it. So first of all, what we need to do is work out the height of this triangle. Okay, and we can do that by using Pythagoras. So this height here, using Pythagoras, the hypotenuse is 2. Okay, so we're actually forgetting now about this other triangle. So what I'm going to do, just to make sure it's not confusing anymore, I'm just going to remove this one and focus on the one I've got left over here. Okay, so just looking at this one. So using Pythagoras, hypotenuse squared equals that side squared plus the height of this one squared. So 4 equals 1 plus the height squared. So 3 equals, in a different colour actually, take one from both sides, we get 3 equals the height of it squared. Therefore the height will equal the square root of 3. Now we can think about what tan 30 is. So tan is opposite 1 divided by the adjacent, which is root 3. So we know tan 30 is that, just by using the triangle we've constructed. And we can now think about sine 60. So sine 60, sine is a saw, opposite, so opposite to the angle 60 is root 3. And h, hypotenuse is 2. So sine 60 is of course root 3 over 2. So therefore tan 30 multiplied by sine 60 that's 1 over root 3 multiplied by root 3 over 2, and in the same way the root 3 on the top and the bottom will cancel each other out, and we're just left with 1 on top, 2 on the bottom, which is 1/2. Question 15. We have a solid shape and it's a cone on top of a hemisphere. Hemisphere just means half of a sphere. So given some information here, the height of the cone is 10, the base of the cone has a diameter of 6, hemisphere has a diameter of 6, the total volume is k pi cm cubed, where k is some integer rather, we need to work out the value of k. Well, we need to work out the radius for the diameter. Okay, so if the diameter is 6, that tells us that the radius of both the cone and the hemisphere is equal to 3. Okay, so we know that r radius is 3. So we can fill this in these formulas here. Now, of course, at the bottom, this is just a hemisphere, it's not a full sphere. So we can adapt this formula here. If the volume of the sphere is 4/3 pi r cubed, then a hemisphere will be exactly half of that. Half of 4/3 is 2/3. So the hemisphere will be 2/3 pi r cubed, where we've now worked out the radius. The radius is 3 because it's half of the diameter, which we've been told is 6. Also, as well, to work out the cone volume, we need h, which is the height, and we are told that the height of the cone is 10. And we're also told the total volume of this shape is k pi cm cubed. So the total volume in total, the total volume equals volume of the hemisphere plus, of course, the volume of the cone on top of it. So that's going to be, for the hemisphere, we're going to have 2/3 pi times the radius, which is 3 cubed, so that's for hemisphere, and plus the volume of the cone, which is 1/3 pi times r squared. Well, radius is 3, so that's times 3 squared times the height, which is 10. So this can be simplified somewhat. So 3 cubed is 27. So 2/3 of 27. We can work this out after, actually. I'll just do it in a few different steps. So 2/3 pi times 27 plus 1/3 pi. 3 squared is 9. 9 times 10 is 90. So 2/3 times 27. 2/3 of 27 is going to be 18. 1/3 of 27 is 9, multiplied by 2 for 2/3. That's going to be 18. So that's going to be 18 pi. Then 1/3 of 90 is 30. So 1/3 of 90 pi will be 30 pi. So that's going to be 48 pi cm cubed. But of course, as good as that is, we've not technically answered the question. The question here is, what is k? Well, k is the coefficient in front of a pi. K is just for stuff in front of a pi, which is 48. So we need to say that therefore k equals 48. And then and only then are we done. Question 16. Question about combinations. So it's in a way probability. Can be considered like that. So there's 3 dials on a combination lock. Each dial can be set to one of the numbers 1, 2, 3, 4 or 5. A 3-digit number, for example 553, is just one of many ways. So the examiner's given us one way so we understand the question. So it says work out the number of different 3-digit numbers that can be set for the combination log. Okay, so the quick way of doing this is to think about how many combinations there are for the first one. The first one, there's 5 combinations. The second wheel, the second dial, also has 5 combinations. So in total, that's going to be 5 times 5 combinations. And the third one is another 5 combinations. So in total, it's 5 times 5 times 5, 5 cubed. It's going to be 125 combinations. That's the quickest way of doing it. But what I'm going to show you now is another way, which is slower, but again, slow but sure is better than struggling and getting nowhere. What I'd suggest doing, if you're really stuck, is just consider examples for the first dial being 1. So consider possibilities of first dial being, let's just say 1. This is an optional thing. If you get the first way, great. You don't need to worry about this so much, but just in case you're not convinced by this, or you're thinking, well, I understand that with you saying it, but in an exam I'm not confident I'd arrive at that, think about it the slow way around. So do them in order of size. What's the smallest number you could have? Well, the smallest number would be for all 1s. 1, 1, 1. The next smallest number would be 1, 1, 2. Then 1, 1, 3, and 1, 1, 4, and then 1, 1, 5. To go bigger than 1, 1, 5, we can't go to 1, 1, 6. To go bigger than that, we'd have to change the middle dial from a 1 to a 2. So you'd have 1, 2, 1, 1, 2, 2, and so on. We get to 1, 2, 5. The next number bigger than 1, 2, 5, can't go to 1, 2, 6 because there's no 6. And he changes middle one from a 2 to a 3. So hopefully you can see a pattern emerging. And maths, if nothing else, is all about beautiful patterns. Next, you can probably guess it now. 1, 4, 1, 1, 4, 2, 1, 4, 3, 1, 4, 4, 1, 4, 5. And finally, 1, 5, 1, 1, 5, 2, 1, 5, 3, 1, 5, 4, and 1, 5, 5. So you can see here, I've got 5 rows of 5. So for the first dial being a 1, that's 25 different combinations. So you've got 25 combinations per each digit your first dial is. So 25 combinations for it being a 1, 25 for it being a 2, 25 combinations for the first one being a 3, 25, 25. And so it's going on and on. 25 times 5 would be 125. That's another way of thinking about the same thing. Part B, it says how many of the possible 3-digit numbers have 3 different digits. And again here you can use a symmetry of the first dial being a 1, then apply the same logic to the second dial being, the first dial being a 2, 3, 4 or a 5. So to remind you what we had from the first part, part A, Here's what we had. Those are the combinations, all the combinations of where the first dial is equal to a 1. Now let's just have a look and inspect how many of these numbers have all three digits which are different. Well, the first row here, the first two digits are both a 1, so there's none here in this first one. We can go to the second line now though, not that one because 1's repeated, 2's repeated, but 1, 2, 3, that works, as does 1, 2, 4, and 1, 2, 5. That's got a 1 repeated, 1, 3, 2, that works, 3's repeated, 1, 3, 4, and 1, 3, 5, that works too. Down here, 1's repeated, that's no good, 1, 4, 2, that works, 1, 4, 3, that works as well, 1, 4, 4's got a 4 repeated, 1, 4, 5, all digits are different there. The last one, 1's repeated, so no, 1, 5, 2, that works, 1, 5, 3 works, as does 1, 5, 4, 1, 5, 5 doesn't because the 5 is repeated. And so from this one here, how many have got different digits? 3, 6, 9, 12. 12 combinations. With different digits. But of course, this is just for the case where the first number on the first dial is a 1. So when the first numbers are 1, there's 12 combinations of different digits, but of course that first number could be a 2 as well, or a 3, or a 4, or a 5. So the total number of possible 3-digit numbers with different digits for each one would be these 12 here, when the first dial is a 1, multiplied by 5, because that first dial could have been a 1, 2, 3, 4, or a 5. So it's 12 per first number, and because there's 5 different first digits, 12 times that 5, 12 times 5 gives us 60 combinations. And there's another way we could approach this problem as well. We've got the solution, so I'm going to underline it here, but I'm just going to link it to probability. And we can use probability and link it to the answer from part A. So part A, we realised there are 125 different combinations. So just as a alternative, I'll just put a line under here. Let's consider the probability of picking a number at random, or picking one of these 125 combinations, and there being a digit, so being a number where each digit is different. So what's the probability of picking a number with all different digits? Well, the first digit could be anything. But what this means is the second digit must be different to the first. The first digit could be anything. The second digit would have to be different to the first. And then, so multiply, and then the third digit would have to be different to both the first and second. So to put this into, excuse me, put this into numbers, if the first digit is anything, the chance that the second digit is different means the second digit would have to be one of the 4 out of 5 other digits to choose from. So for example, if the first digit is a 1, the second digit has to be either a 2, a 3, a 4, or a 5. And then the third digit has to dodge and be different to whatever digit the first and the second were. So that only leaves 3 options, out of 5 for the third digit. Multiply this together, we get 12 out of 25. So in other words, 12 25ths of all the combinations will have it where each digit is different. So work out that fraction of the total, and remember from part A there are 125 different combinations. So 12 25ths multiplied by 125 would again give us 60 combinations. That's just a different approach we could use to solve this question. Question 17. We're told that the ratio of x squared to 3x plus 5 is 1 to 2. We now have to find the possible values of x. So what this means is 3x plus 5 is twice as big as x squared. So we can write this down, because the 3x plus 5 part, the 3x plus 5 part is twice as big as the x part. From here, we can deduce that 3x plus 5 must equal 2x squared. From here, we can now rearrange this into a quadratic in the standard form. So we get 2x squared minus 3x minus 5 equals 0. So this is a quadratic which we can solve in a few different ways. We could use a formula, we could complete the square, we could even factorize. So I'm going to show each of the main ways of doing this. So section this out now. So the first one I'm going to do is to show you how to factorize it. Now, this is what's called the AC method. So what we need to do here is to multiply the leading term of the x squared and the constant term at the end. So if we multiply the 2 by the negative 5, we get negative 10, and the coefficient of the x term is minus 3. So what we need to do now is to consider and think of if we can find two numbers that multiply together to give us minus 10, but when we add them up, we get this minus 3. Okay, so we're talking negative 10 because 2 times minus 5 is negative 10, and minus 3 from the fact that the coefficient of x is minus 3. So a bit of brainstorming, a bit of thinking. Hopefully you'll arrive at the conclusion the two numbers we need are 2 and minus 5. And from this, we can rewrite this as 2x squared. The minus 3x now is changed to a 2x and a minus 5x. Now what we can do, what we should need to do, is to split this into two groups. So this first group here, we can factorize out a 2 and an x. In brackets we get x plus 1. We then do the same with this last group. 5 is a common factor of both of these, and both are negative, so indeed we can even factorize out minus 5. The objective here of this AC method is to duplicate what's in the brackets twice. And again we get x plus 1. So we have 2x lots of x plus 1, minus 5 lots of x plus 1, means altogether we have 2x minus 5 lots of x plus 1. And that equals 0. Therefore, Either this bracket is equal to 0, in which case x would have to be 2.5, which writes 5 over 2, or just 2.5. Or maybe this bracket's equal to 0, in which case x would equal -1. That's if you wanted to factorise it. You may have wanted instead to have gone by the completing the square root. And so we're going to start at this point again. So we have 2x squared minus 3x minus 5 equals 0. Now when we complete the square, the leading term of x squared needs to be just 1. So we need to divide everything by 2. We then get x squared minus 3 over 2x minus 5 over 2 equals 0. We're now going to put this bit here inside brackets. We're going to complete the square on this bit. And the way we do this is we take the x squared, and in the brackets just put 1x. The coefficient of the x, which is minus 3 over 2, we halve that, so it becomes minus 3 over 4. And square that, when we minus off this term here all squared. So 3 over 4 all squared is 9 over 16. But of course we have a minus 5 over 2 as well to consider. And that equals 0. So we need to neaten this up slightly, but we're on the way to solving it using the completed square method. So we're now going to have x minus 3 over 4 squared, and this here can be put over a common denominator of 16. If we multiply the 2 by 8, it becomes 16. We can then multiply the 5 by 8 as well. So this here would become 40 over 16. So minus 9 over 16, minus another 40 over 16, that's minus 49 over 16. If we add that to both sides, we now get this, 49 over 16. We can now square root both sides. So x minus 3 over 4. Remember to do plus or minus as well, always important this. Plus or minus a square root of 49 over 16. But because both numerator and denominator are square numbers, we can square root both. So square root of 49 is 7, and the square root of 16 is 4. Therefore, if we add 3/4 to both sides, x equals 3/4 minus 7 over 4, or x equals 3/4 plus 7 over 4. Now this could be simplified. 3/4 minus 7/4 is minus 4/4, which is minus 1. And over here, 3/4 plus 7/4 is 10/4, which is 5/2, which is this solution had here, which is 2.5. So again, we get exactly the same as what we had from before, which of course was what we'd expect. And the third main option is we can use the quadratic formula. So using the formula, we have 2x squared, so I'm going to write this in the blue, so 2x squared minus 3x minus 5 equals 0. So the quadratic formula goes for x equals minus b, So minus 3 plus or minus the square root of b squared, so that's minus 3 squared, minus 4 times a times c, that's 4 times 2 times minus 5, all over 2a, which is 2 times 2. Oops, wrong colour. So if we neaten this up, we'll be good to go. So minus 3, that's plus 3, plus or minus the square root of this. Well, minus 3 times minus 3 is 9. Minus 4 times 2 times minus 5, it's going to be plus 40. So 9 plus 40, that's the square root of 49, all over 4. So in other words, x equals 3 plus or minus 7, because the square root of 49 is 7, all over 4. So therefore, either x is 3 minus 7 over 4, which is minus 1, or x is 3 plus 7 over 4, which is 10 over 4, which again is 2.5. So whichever way you want to do it, take your pick. As we've seen, always will work. Question 18, part A. Express root 3 plus root 12 in the form a root 3, where a is an integer. So what we need to do is to get root 12 in the form something root 3. Well, 12 is 4 times 3. So we can rewrite 12, the square root of 12 rather, as root 4 root 3. However, the square root of 4 is obviously 2, so this is root 3 plus another 2 lots of root 3. 1 lot of root 3 plus another 2 lots gives us 3 lots of root 3. And that's our final answer for part A. Part B, express this in the form root b over c, where b and c are integers. So 1 over root 3 to the 7. So we just raise the top to the power 7 and the bottom to the power 7. So this now can be done just by remembering the laws of indices. So 1 to the 7, I'm just going to leave as 1. But the square root of 3, a square root is the same as being 3 to the power of a half. So this means 3 to the power half to the power 7. When you're doing the power of a power, we multiply the powers. So power half multiplied by power 7 becomes power 7 halves. So next up, 7 halves is the same as 3 and a half. So this is the same as 3 cubed multiplied by 3 to the half. So next up, what we're going to have here is we're going to have 1 over 3 cubed is 27, 3 to the half is root 3. So it's 1 over 27 root 3. However, we want the bottom number to not have a root in it. The top number can have a root, but not the bottom. So we need to remove any square root from the bottom. So what we need to do to both top and bottom here is multiply both by root 3. And if we do that, 1 multiplied by root 3 becomes root 3. 27 times root 3 times another root 3 becomes 27 multiplied by just 3. And 27 multiplied by 3 is 81. So we end up finally with root 3 over 81. Question 19. We're given that x squared minus 6x plus 1 equals x minus a, all in brackets squared, minus b for all values of x. We need to find the value of a and the value of b. Now this is a question asking you about really asking you. Indirectly it's asking you to complete the square. So what we need to do here is to change it from expanded form into this form, which is completed the square. And that's the wrong colour, so let's start with a black font. So x squared minus 6x plus 1. How do we complete the square? Well, it's quite procedural really. So all we need to do is we take the x squared of the minus 6x. We take the x stuff, to be crude about it, and we manipulate it. Double check that the coefficient of x squared is 1. There's only one x squared. There is, so we're fine. Open up the brackets. Instead of x squared, we put 1x. We look at the coefficient of the x term, the stuff in front of the x. It's minus 6. We halve that into minus 3. Close brackets and square. We then always have to minus off this minus 3 part squared. So we minus off not minus 3, but we subtract away minus 3 multiplied by minus 3, which is positive 9. So we minus off that positive 9, but of course we'll have that plus 1 at the end. So neating it all up, we get x minus 3 squared, and minus 9 plus 1 overall is minus 8. And so as we can see here, our a is 3, and our b is 8. So a is 3, and b is 8. Now for part 2 it says write down the coordinates of a turning point on the graph y equals x squared minus 6x plus 1, which we've just shown is the same as x minus 3 all squared minus 8. The turning point of a quadratic is given essentially by the completed square form of it. The turning point of this is what we're subtracting away from x in the bracket. So the turning point is plus 3 for x, but just this number on its own for y. So this turning point will happen when x is 3 and y is minus 8. And we can think of it like this. What value of x would minimize this curve? Well, anything here squared is at least 0. You can't have something negative after you've squared it. So the minimum this thing could be is 0. It's going to have a minimum when x is 3, because when x is 3, this bracket will be 0. 3 take 3 is 0. So the minimum point will be when x is equal to 3, and when x is equal to 3, y will equal 0 squared minus 8, which is just obviously minus 8. So that's the turning point when x is 3 and y is minus 8. Question 20, we're talking about inverse proportion and direct proportion. So the first two lines are key to solving this one. So it says h is inversely proportional to p. So what this means, the proportionality sign is like a fish. So h is proportional, in fact inversely proportional I should say, my apologies. If it were proportional to p, we'd write this. However, because it's inversely proportional, we write it as 1 over what it's inversely proportional to. So h is inversely proportional to 1 over p. So we can change this proportionality fishy looking symbol to an equals by writing h equals, and we take this here and multiply it by some constant we need to find. I'm going to call the constant little k. So k times 1 over p becomes k over p. So h equals k over p, where k is some constant of inverse proportionality for us to find. We're also told this here, that p is directly proportional to root t. So just as we had that h was inversely proportional to p, now we're told it's directly proportional to t. So from here we can write that p is proportional to the square root of t, then replacing the proportionality symbol of an equals, we can say that p therefore must equal some other constant of proportionality multiplied by root t. We've used little k for the symbol of proportionality in this equation, so we need a different symbol because it's not necessarily the same constant for these two different equations. So I'm going to call this big K here, so big K root t. Now we're given some extra information here. It says that h is 10 and t is 144 when p is 6. So I'm going to call this one equation 1 and this equation 2. So we're told h is 10 when p is 6. So we can sub h equals 10 and p equals 6 into equation 1. We then get h is 10 equals k over p, which is 6. So therefore k must be 60. And therefore equation 1, because you know what little k now is, it's 60, we can write that h equals 60 over p. We can also substitute t as 144 and p as 6 into equation 2. So let's substitute t as 144 and p as 6 into equation 2. So if p is 6, then p, which is 6, equals k, big K, root t, but we're told that t is 144 when p is 6. So 6 equals k times root 144, but the square root of 144, you should know, is 12. 144 is a square number, it's 12 squared. So 6 equals 12k, therefore k equals 6 divided by 12, which is a half. And so equation 2, we can write p equals root t over 2, or just half root t. So we can link this bit together with this bit now. We want a formula for h in terms of t, so we want h equals something. So we can link these two together. Now, we now know what p is in terms of root t. So we want here to replace p, we want a formula for h in terms of t. It doesn't mention anything about p as such. So we can replace p with root t over 2. So from these two bits, which we've linked together, give myself some more space over here, we can say that h equals 60 divided by root t over 2. Now, I think having a fraction where you've got a fraction within a fraction is quite confusing. So what I'm going to do here, to get rid of this fraction on the bottom, on the denominator, I'm just going to multiply both the top and bottom by 2. So in other words, h equals 120 divided by the square root of t. And that will actually do us. That's an equation that links both of them together. The formula for h in terms of t, h equals this. H is 120 over the square root of t. Question 21, part A. I'm going to show you two different ways of arriving at the same thing. We've got two different functions, f of x and g of x. First part, we need to find the inverse function of x. So f minus 1x means the inverse of f of x. So just write that down now. That's the inverse of f of x. It doesn't mean 1 over f of x. It's just notation for how to go back to the original input if you worked out an output. So what I'm going to show you first of all is one way of doing it. So let y equals f of x. Then instead of saying f of x equals 3x minus 1, I can say y equals 3x minus 1. Now what we do to find the inverse is we change it from y, the output, being the subject, to making x, the input, as a subject. So what we can do first of all is add 1 to both sides and get y plus 1 equals 3x. Then if we divide both sides by 3, you can see that x will equal y plus 1 divided by 3. Now this final step can confuse people. Instead of putting f minus 1x equals y plus 1 over 3, you still need to put it in terms of x. So switch the y for an x. So y plus 1 becomes x plus 1, leave everything else as it is, and we've got it. And that's what we have. Another way of getting the same thing would be, because this is a linear function, we can do this, we can use a function machine. So start with the input, which typically is x. So think about what f of x is. Then what we're going to do is reverse absolutely everything, and what we'll end up with is f minus 1 of x. So starting with the input, how do we obtain f of x? Well, the first thing we do here is we take x and multiply it by 3 to give us 3x. After multiplying it by 3 to get 3x, we then take away 1. So x, 3x, 3x minus 1, that is what f of x is. What we're going to do now is we're going to start at the opposite side, going the opposite way, and we're going to do the opposite things to undo what's been done. That gives us the inverse. The inverse just undoes the function we had. So now we're going to input at the other end, but rewind back to the start, undoing the operations by doing the opposite things. So here, instead of subtracting 1, we're going to add 1. Instead of multiplying by 3, we're going to divide by 3. And then at the end, we're going to have x plus 1 divided by 3, and that is f minus 1 of x. So that's how we can get f minus 1 of x a different way, by using a function machine. Part B, we're told that f g of x equals 2 lots of g of f of x. Now that's a bit of something to get your head around first before part B. So let's just think about what f g of x actually means. Well, f g of x means we're going to apply the function x, the f of x, to an input which now isn't x. The input now is g of x. So it's f of g of x. Now g of x is x squared plus 4. So the input isn't just a normal x, it's now x squared plus 4. So now let's think about what f of x does. Whatever you put in to the function f, it multiplies it by 3, and then we subtract 1. And so our input now isn't just an x, it's x squared plus 4. So that's going to be 3 lots of x squared plus 4 minus 1. So that's expanding the brackets, we get 3 lots of x squared. 3 times 4 is 12 minus 1. So we get 3x squared plus 11. So that's what fg of x actually is. Next, we need to think about what 2g f of x would be. Well, 2g f of x. Well, this is going to mean 2g of what f of x is. So the input now for g isn't x. Our input for g now is actually f of x, which is this. So it's 2g brackets 3x minus 1. So what does the function g do to its input? Well, the input here, in this case it's an x, gets squared, and then we add 4 to it. Now though, we're not doing g of x, the input here is 3x plus 1. And so x squared is going to become this whole thing squared. Remembering as well not to forget the 2, that was almost a fatal error by me. It's 2 lots of g, so 2 lots of the input squared plus 4. So that's 2. Now 3x plus 1 all squared, that's 9x squared. We multiply 3x by the 1 and double, that gives us 6x. 1 squared is just 1, plus 4. So that's going to be 2 lots of 9x squared plus 6x plus 5. Apologies, it was minus 1, wasn't it? So what I need to do here is switch this to a minus, apologies. So this will still work. Sorry, I just spotted that. I had a few distractions going on around me. I apologise. So now we're going to get 9x squared minus 6x. Then 1 plus 4 is plus 5. And finally, multiply all this by 2. We get 18x squared minus 12x plus 10. And that's what 2 lots of gf of x is. So therefore, fg of x, which is 3x squared plus 11, must equal this, which is 18x squared minus 12x plus 10. just using what the question told us. So we're nearly home and dry now. We want everything onto one side equaling 0, and so if we subtract 3x squared plus 11 from both sides, then this side in yellow will end up being 0. I'm going to write that last. This side here, 18x squared minus 3x squared gives us 15x squared. Minus 12x stays as it is. We're not taking away any other x's. 10 minus 11 gives us minus 1, and that equals 0 as required here. So a slightly complicated one on that one, but that's all we need to do. So question 21 is over and done with. So we come to the last question on the entire paper. So it's quite a tricky question, it looks like. I'm going to show you 3 different ways of solving it. The first way is actually going to be a way which I wouldn't recommend you try first of all. It's going to be trial and error. I'm showing you this way first because if I showed it you last, it would sort of ruin the big reveal of what the solution is. And this, I think, is the most powerful way of showing how to tackle a problem if you're really stuck in terms of knowing what to do in an exam high-stress situation. So anyway, let's read the question. So there's only R red counters and G green counters in this bag. So they're either red or green. The counter's taken at random. The probability the counter is green is 3/7. So therefore, green to red, green we have 3/7, so the other 4/7 must be red. If we then multiply both sides of this ratio by 7, you can fairly clearly see that the ratio of green to red must be 3 green for every 4 red. So that's going to be a useful thing to consider. Anyway, so probability of the counters green is 3/7. It's then put back into the bag. Afterwards, 2 more red counters and 3 more green counters are put into the bag. A counter is taken at random again from the bag, but this time the probability of the counter is green is 6/13. Find the number of red counters and the number of green counters that were in the bag originally. So we need to find G and R, essentially. Now, the probability that a green counter is picked at the end is 6/13. So at the end, the probability of being green is obviously going to be the number of green counters all over the total. So we can put this into an equation of sorts. So probability of being green, well, number of green counters, 3 more green counters were added. There were G green ones to begin with, and 3 more green have been added. So the total number of green after another 3 have been added is G plus 3, and the total number of counters altogether must be G plus 3 plus R plus this extra 2 red. So that becomes G plus 3. This is G plus R plus 5. And that must equal 6/13. So that's our starting point, and that might be confusing in terms of knowing what to do with information. At this point now, though, we can think about carefully following a trial and error approach. So let's now think about how we could perhaps do this. So we know that the ratio of green to red, initially, G to R, must have been 3 to 4. So this can be our starting point. So let's assume that maybe there were just 3 green and there were just 4 red. Now, if that was the case, we can add this to a table. So let's assume that there might have just been 3 green and 4 red to begin with. Now, we don't know if this is going to be true or not, but we can try it. So if there were 3 green, and then 3 more green were added, 3 plus 3, G plus 3 would become 6. And then if 2 more red counters were added, R plus 2 now becomes 4 plus 2, which is 6. Then the probability of picking a green, which is this expression here, we're told this needs to equal 6/13. So we can see if it does, and if not, we can improve our initial guess. So G plus 3 is 6. And then G plus R plus 5 is just these two columns added together. So 6 plus 6 is 12. 6 out of 12 is a half. Is a half 6/13? Obviously not. So there couldn't have been 3 greens and 4 reds to begin with. G can't be 3, R can't be 4. So what could G and R have been instead of 3 and 4? So we were still in the ratio of 3 to 4. Well, 3 dot dot 4 would be the same as 6 dot dot 8. So maybe there could have been 6 greens and 8 reds. 6 to 8 would simplify down to 3 dot dot 4. So let's try this next. In this case, G plus 3 would be 6 plus 3, which is 9. R plus 2 would be 8 plus 2, which is 10. Then what we're going to have is G plus 3, which is 9. G plus R plus 5 is the grand total of these two columns, so 9 plus 10 is 19. 9/19 would not simplify to 6/13, so again that one can't be right either. But keep going. Equivalent ratios of 3 to 4. We've tried 6 and 8. 3, 6, 9. Let's try 9 dot dot 12. In this case, G plus 3 would be 9 plus 3, which is 12. R plus 2 would mean 12 plus 2, which is 14. Now, for probability of picking a green, this fraction here would be G plus 3, which is this column here, which is 12. And G plus R plus 5 are these two columns added. So 12 plus 14 is 26. Both numbers are even, so we can half them. 12 halved becomes 6. 26 halved becomes 13. And what would you know, that tends to work. So we've cracked it, we've solved it, which is great. So the number of red counters and green counters there must have been, because we've done this, we've worked it out. So the number of green counters initially must have been 9. And the number of red counters must have been 12. So G is 9 and R is 12. And that's the solution. It does not say you can't use trial and error. That's absolutely fine, and we're done. Now, I did mention that's not the way I would have taught it. Could we do it without guesswork? But I just wanted to show you there that the worst thing you can do in an exam situation is nothing at all. If in doubt, have a stab. Trial and error can be used pretty much any time really if you've got a calculator. If you've not got a calculator, it can be reserved for occasions when you know the answer is going to be a smallish number, not like millions or billions, and the numbers are easy to deal with, typically whole numbers or integers. Let's have a look now at a different method. So, of course, I'm not just going to do a solution of an exam paper without telling you how to solve it directly in terms of R and G. So, let's think of it now, solving it directly. So, starting afresh, we're told here probability of picking a green counter is 3 out of 7, and therefore the probability of picking a red must be 4 over 7. So just to get this in terms of a equation relating R and G, probability of picking a green is going to be the number of green counters there were, which is G over the total number of counters, which to begin with would just be R plus G. And we're told that's 3 over 7. So we can solve this equation next by cross multiplying. So from this, G times 7, 7G, equals 3 lots of R plus G. Expand the brackets, we get 7G equals 3R plus 3G. Subtract 3G from both sides, we get 4G equals 3R. Now if you divide both sides of this by 4, we can see that the number of green, G, must be 3/4 of R, which is what we said to begin with in part A, sorry, method A, number of green is 3/4 number of red. That's the same as saying the ratio of green to red is 4 to 3. So we're going to use that and return to it. Now later on, we're told this. 2 more red counters and 3 more green are now put in the bag. Then after, the probability of picking a green is 6 over 13. So now, after this new information, the probability of picking out a green one will be the number of greens, which is now G plus 3. So it would be the number of green out of the total number of counters. So now the total number of counters is R plus G, which is the initial number. But because 2 more reds are added and 3 more greens, 2 plus 3, that's an extra 5. And that's now 6 over 13. So now, similar to what we did before, we could cross multiply this. And if we do that, just give myself a bit more space. 13 lots of G plus 3 equals 6 lots of R plus G plus 5. Expand the brackets. 13G, 13 times 3 is 39, equals 6R plus 6G plus 30. So let's get things onto one side. And so if I take away 6G from both sides, I'd have 7G plus 39 equals 6R plus 30. If I then subtract 30 from both sides, I get the 7G plus 9 equals 6R. But now we can use this. But from before, we knew that G is 3/4 R. So we can use this to our advantage. So because G is 3/4 R, we can substitute this. So 7G is actually 7 lots of 3/4 R plus 9 equals 6R. So if we multiply this out, we get 21R over 4, or 21 over 4R, plus 9 equals 6R. We can then get the r's onto the same side of the equation. 21/4 R. 6R, well 6 is 24 quarters. So I'll just make a note of this. 6R is the same as saying 24 over 4R. Now this is a useful thing to remember because this can simplify it for us into just one fraction. 24 over 4R minus 21 over 4R leaves us with 3/4 of an R. Okay. Now we can rearrange this. So if we multiply both sides by 4, we get 36 equals 3R. Therefore, divide through by 3. We see that therefore R must equal 36 divided by 3, which is 12. So now we know this, we can then work out how many greens. So because green is 3/4 R, the number of green, that's going to be 3/4 of the number of red, 3/4 of 12, which is obviously going to be equal to 9. So again, R is 12 and G is 9. A third and final way of doing this, we can directly solve it using ratio. And so, going back to what we said at method C, we've got here that probability of being green is 3/7. So the ratio of green to red, if 3/7 are green, the other 4/7 are red. So we've got 3 lots of green to 4 lots of red. And so the question now is, how much is a lot? 3 lots of green, 4 lots of red. So now I'm going to say let one share be known as X. Okay, so green to red is essentially 3X to 4X. It's very similar to method B, but I think you'll find this one a bit more straightforward. So next, the probability of picking a green finally is 6/13. So probability of picking green is going to be the total number of greens, which is now 3X plus the extra 3 greens. So 3X plus 3. And the total number of counters now, after these 3 more green counters and 2 more red were added, was the initial 3x lots of green and 4x lots of red, which was 7x, plus these extra 3 plus 2, which is 5 extra counters. And we're told that's 6 over 13. We can now solve this for x. Then once you worked out x, multiply it by 3 to work out the number of green originally, multiply x by 4 to work out the number of red initially. So this for me is a more fitting way of doing it. So if we cross multiply, and again give myself a bit more space, so 13 multiplied by 3x plus 3 equals 6 multiplied by 7x plus 5. Expand the brackets. 13 times 3x is 39x. 13 times 3 is 39. 6 times 7x is 42x, and 6 times 5 is 30. If we subtract the x's, 39x, from both sides, we get that 39 equals 3x plus 30. Now we can subtract 30 from both sides, which gives us 9 equals 3x. Therefore, x equals 3. So the number of red, so r equaled 4x, which is 12. And g equaled 3x, which is 3 times 3, which is 9. And that's all we have to it. That solves the last question of the exam paper, and therefore we're done. I hope you found this useful. If any questions been at all a bit confusing or could be explained a different way you feel, let me know and I'll do my best to clarify that. Leave comments in the comment section, keep them polite if you can please, that'd be great. And please do consider subscribing because I'll be uploading new videos from time to time. Thank you very much for watching. As I say, hope this has helped, even if a minor way. Check back soon and take care for now. Goodbye.